Today we're going to continue with the basic gates with the NAND and NOR gates. The NAND gate the 7400 the symbol is a AND gate with a negative output, and the state table is identical to the AND gate, except for it's reversed. The outputs are inverted. So the state table looks like that. It is the opposite of a AND gate. It's high when one or both of the inputs are low, and low if both inputs are high. The schematic of it, in its most basic form, looks like so. It looks like on the internals, looks like a AND gate without the inverter. So it's actually a simpler gate on the component level. What makes the NAND gate and the NOR gate special is they are universal gates. From the NAND gate, you can do any logic circuit using just NAND gates. To show this, if you look at the state table, if you tie both inputs together, you have low on the input, high on the output, high on the input, low on the output, which is what an inverter does. So the NAND gate can be used as an inverter. Because it can be used as an inverter, you can put an inverter after a NAND gate and use it as an AND gate. So there's your second of your most basic gates. Now, a little less obvious is if you invert the inputs you get an OR gate. So you can use two NAND gates as inverters on the two inputs of a NAND gate and create an OR gate. And from the inverter and OR, you can create any logic circuit. Therefore, you can create any logic circuit with just NAND gates, thereby making it a universal gate. As a little bonus, there's a nice little way to create a XOR gate. Using 4 NAND gates. I'll leave the tracing the inputs and inputs to the output as an exercise for you to verify that that is truly what this schematic would yield. All right, just the snoring. Anyway, so the NOR gate, or NAND gate, sorry, can be used to create any of the variety of gates alone. Sometimes it uses fewer transistors, sometimes it doesn't. We'll get into the NOR gate. Yeah. Oh, an OR gate? Well, let's look at the state table. All right. So you have A and B, and then you have A prime, and then B prime, and then you have the A prime NANDed with B prime. Okay, so you got low, 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 high, high, low, high, high. So A prime would be what you get after this. This is an inverter. X is an inverter. So A prime is A, H, H, L, L, just the inversion of these inputs. B prime would be H, L, H, L. Now, those are inputted into a NAND gate. So the two inputs being high would yield a low input, low output. High, low gives you high. Low, high gives you high. And low, low gives you high. And, oops, sorry. So the result is the equivalent of an OR gate. Got it? All right. Here we got, let's see here. And we'll move on to the NOR gate. That is an OR gate symbol with the inverted output bubble there. And the state table is the inverse of an OR state table. So it's high when both are low, and low when either one of them is high. Okay. And again, that's the 7402. And the simple schematic of that looks like so. Looks like the OR gate with the transistors in parallel without the inverter after it. So it's at 1/3 less transistors than the OR gate. This is also a universal gate. Because if you tie the two inputs together and it's low, you get a high. Both inputs high gives you a low. So the inverter is just a NAND and NOR gate, with the inputs tied together. And an OR gate would be a NOR with another NOR acting as an inverter. And similar to the NAND implementation of the OR gate, the NOR implementation of an AND gate is invert the inputs and run them through a NOR gate. Oh, that's the AND. In a Boolean expression, we'll look at the Boolean expressions, give you a chance to get all this down, how these are expressed. NAND and NOR do not have individual symbols for them. So let's see here. Just about caught up copying it down. Okay. Now start erasing over here. Now, in a Boolean expression, NAND A dot B with a bar over all of it. The bar indicates that it is a inverted output. NOR would be A plus B with a bar over everything. And this could also be AB with a single bar, or A star B with a single bar. Either way, it can go either way. Depends on the style of writing you want to do. Alternatively, anybody need the schematic anymore? No? You can, if you're on your computer and can't do the bar over the letters, you can do A prime, A star B quantity prime, A dot B prime, and A B prime, and then A plus B prime. The prime is done first, so if you do not include the parentheses in these cases, you would have A star B prime without the parentheses, or A plus B prime without the parentheses. So to express the NAND, it would be with the NAND and the NOR, you would use the parentheses if you're using the prime notation. All right. Let's see here. Just for the sake of completeness, when I described the exclusive OR gate last time, I did not give the symbol that is used in Boolean expressions for that. You don't see it often, but it is out there. It is A plus with a circle around it, B. For the sake, like I said, for the sake of completeness, you'll see that in data sheets for processors and that sort of thing later on in the curriculum. Not likely in this class, but you will see it in the practical world. Any questions about the NAND or NOR gates? They're fairly simple gates. The basic concepts of the various gates are simple in concept, but can be put together to make very complex structures. Yeah. Sure. All right. Let's go ahead and put up the state table for the NAND gate first. right? No, high. That's NOR. Yeah, so there's the state table and the schematic for it. Let's go ahead and now let's go ahead and trace through and get the state table for the XOR. You got A, B, XOR. Okay, if they're both low, these are both low, this will be high, this will be high, this will be high, this will be low, this will be low because it's connected here. So if these are both going to be high, because of the low-high input and the high-low input, and then this is going to be high, and the output here will be low. So the output would be low. With me so far? Okay. Now, I'm just going to do one of these because it works. It's symmetrical, so it will work the same either way. Low and high. Low and high on here will be a high output here, and low here will be and a low here and a high here will give you a high output on this one. A high here and a high here will give you a high, will give you a low on the output here. And then the last one will be a high and a low, will give you a high output. And just flip it, the mirror image of it, it does the same for the high A and low B. So it'd give you still give you a high output. All right. Now, if you have both high, this output will be low because of the NAND gate. This will be high, and low will give you high here, and likewise low here and high here will give you high here, and the high and high on the last gate will give you a low here. To give you a low down here and give you the exclusive OR gate effect. I'm probably not going to test you on this diagram, but I just keep it in your notes. If you have it, if you memorize it, great. If you don't, I happen to have it memorized, but that's because of years of doing this sort of thing. But it's as circuit diagrams go, it's fairly simple. You'll get into much more complicated diagrams in the future, but yeah, it's just a for this. I mainly include it for the sake of completeness, and covering all my bases and all that sort of thing. In digital logic lab, you're only going to be using and, or, and not gates. You're not going to use any NAND or NOR gates that I'm aware of. So as far as the lab is concerned, all of this is just bonus material. It's not going to contribute to your grade in that class at all. But when you get into designing various circuits and stuff later on in your curriculum, the NAND gates and NOR gates could come in handy. So, and XOR. And like I said, the XOR is used later on in this class in the use of adders because of the characteristics that it has. It's one of two gates used to make a half adder. So, but all right. Well, is there any other questions? Want me to cover anything over again or restate something? No? All right. Well, yeah. What was that? Yeah. It's a plus with a circle around it. XNOR would be with a bar over everything. Yeah. Yeah. Those are truth tables, not these are state tables. They're slightly different. No, low would be false and high would be true. Yeah. The convention is to, in logic, which is what is covered in discrete structures, to put the true values first, whereas in digital logic you put the low values first in the rows of the state table. As we'll see later on in the semester, these are called state tables, not truth tables, because the state can change or be in states that you're not you don't know or you don't care. So the state is has more states than just the two. we're just covering the two, low and high at this point. So, yeah. Next quiz. I'm thinking next Friday. Next Wednesday, we're not going to have class. I'm going to be traveling. But Monday, we'll cover some more of the gates and how they're brought together and that sort of thing. And Wednesday off, and then quiz / test or whatever on Friday. All right. Have a good day.